Greetings YouTubers, my name is PhD Tony and this is episode 2 in my series on atmospheric physics. Today we will be discussing the origin of pressure gradients inside Earth's atmosphere, and as a consequence of this discussion we will explore why it is that air gets colder as it gets higher. At this point we're starting to get into the nitty-gritty of thermodynamics and fluid mechanics. And as a result there is some sophisticated mathematics presented in the following material. But it is by no means necessary for the casual listener to follow the mathematics in any detail. It will be sufficient to simply follow the superficial elements of the discussion. I have included the mathematics solely for the benefit of those who want to go into the material in slightly greater depth. So without further ado, let's get started. We consider a fluid that is at rest in its equilibrium position. The lateral boundary conditions for this fluid are supplied by either some form of reaction force or periodic boundary conditions as would apply on the surface of a convex solid. Formally, we may split the fluid into very thin layers. Inside each layer, the density of the fluid and the gravitational acceleration applied to the fluid may be treated as being constant. This is the first of a series of simplifying assumptions that we will make to facilitate our analysis. The validity of these assumptions has been extensively tested by comparison between the results of this theory and observed reality. The close agreement between the results of this theory and the observations, and the close agreement between the results of this theory and more sophisticated theories, suggests that the approximations do not significantly impact the accuracy of the calculations. As I have mentioned in previous videos, all mathematical and numerical models have non-zero error. This is not in and of itself a fatal flaw, as long as the model error is small compared to the uncertainty of the observational dataset against which the model results are being compared. This has been extensively tested by intercomparison between observations and model results for all of the assumptions that will be made in the analysis that follows. The weight of our layer of gas is then the volume of that layer, which is just the area times the thickness, times the density of the gas times gravitational acceleration. We can repeat this calculation for all layers inside the fluid. No fluid has infinite extent, therefore there is only a finite thickness of fluid to be considered in any particular case. Our model allows that a fixed force F0 is being applied at the upper boundary of the fluid being considered. The nature and magnitude of this force is left unspecified and may be adjusted to reflect the circumstances of any physical system being modelled. For instance, Earth's oceans are subject to a force at their upper boundary applied by the overlying atmosphere. At any point inside the fluid, the total force that would be applied to a body at that point is simply F0 plus the weight of the overlying layers of fluid. Since we can calculate the weight of each of those layers in turn, we can just add them all together. That's what that fancy and intimidating looking mathematics at the bottom of the slide is suggesting. Pressure is force per unit area, so once we know the force, we can instantly calculate the pressure by simply dividing by the area A. The formula in the red box is just the incremental change in pressure due to a particular fluid layer. We will be using this formula quite a bit in the analysis that follows. Most liquids are incompressible, and this is certainly true of water. In an incompressible liquid, density is constant. It does not change with position or as a function of pressure. Under these conditions, the formula we derived on the previous slide simplifies. The pressure at any point in the fluid is simply the density of the fluid times gravitational acceleration times the thickness of the overlying fluid plus P0, the pressure due to F0 at the top of the fluid. In applications that require extreme precision, it is necessary that density perturbations due to changes in temperature and salinity be considered. However, as a first-order approximation of equilibrium conditions, the formulation presented here is quite accurate and has been extensively observationally validated for large bodies of water on Earth's surface. Before moving on to the general case of compressible fluids, like the atmosphere, we're going to need to pause for a moment to consider some elementary principles of thermodynamics, in particular the physical mechanisms of heat transport. There are 3 mechanisms of heat transport: convection, conduction, and radiation. Radiation refers to the transport of internal energy via electromagnetic waves. In most near-Earth systems, this transport is in the infrared spectrum. As illustrated in the figure, if you hold your hand towards a stove element, you will feel energy being radiated to your hand from the heated stove element. Conduction refers to the transport of internal heat energy via direct intermolecular collision. When heated, a particle's kinetic energy will increase. That particle will bump against nearby particles, particularly in a solid or a liquid, and will transfer its energy to those other particles. This is why the handle of a pot on a stove will tend to get hot over time. Convection refers to the transport of internal energy via movement of the material being heated. This occurs because of density decrease induced by the heating of the material. In a material with an appropriately loose molecular structure, the heated material will become less dense than the overlying material and will tend to move upwards until it finds its equilibrium level. Convection is by far the most rapid of these three mechanisms of heat transport. However, in order to be efficient, it requires that the material in question be dense enough that physical motion is an efficient form of transporting energy. This is not the case for Earth's upper atmosphere. However, in Earth's lower atmosphere, this is the case, and convection is the dominant form of energy transport in this portion of the atmosphere. For the rest of this presentation, we will be restricting our attention to compressible fluids in which convection is the dominant mechanism of energy transport. We consider now the case of a compressible fluid or gas. Consider a packet of gas at an initial position. In this diagram, that packet of gas is represented by the contents of the red balloon. If the packet of gas is moved to a different pressure, then the gas inside the balloon will either expand or contract. In order to expand, the gas packet must push aside or displace some of the gas surrounding it. In order to achieve this, it must overcome the pressure being applied to it by that gas. In expanding, the gas moves from a lower energy state to a higher energy state. The increase in the internal energy of the gas inside the gas packet per unit mass is simply the pressure times the change in volume divided by the mass of the gas in the packet. Here we have used the letter Q to represent the total internal energy of the gas within the gas packet. We must also consider the contribution of gas temperature to the total internal energy of the gas packet. We now consider a gas packet of fixed volume. If the temperature of this gas packet is altered by an amount dt, then the amount of energy per unit mass required to affect this change in temperature is simply the product of dt and the specific heat capacity at constant volume of the gas. The specific heat capacity at constant volume is simply the amount of energy required to raise 1 kilogram of the gas in question by 1 degree Kelvin. This quantity can be obtained from direct observational experience. The total change in internal energy experienced by a gas packet is therefore the sum of the volumetric effects described in the previous slide and the temperature effects derived in this slide. In practice, there is a third contribution to the internal energy of gas packets in the atmosphere. This is due to latent heat effects, which result from the transport of liquid vapor and their potential for condensation or for further vapor to accumulate in the gas packet. While these effects may be readily included if one is meticulous enough, they greatly complicate the mathematics involved, and for the moment we're going to neglect them. The basic results we will derive in this presentation are unaltered by the inclusion of latent heat effects. So we have derived a mathematical form for the change in internal energy of a gas packet. As we saw earlier in the presentation, material convection is a much more rapid process than either heat conduction or heat radiation. As a result of which, if a gas packet is convected to a higher altitude and then returned to its original position, this will occur with sufficient speed that there is no opportunity for any exchange of energy with the surrounding gas. All of which is a long-winded way of saying that during convection the total change of internal energy of a gas packet, delta Q, is just zero. This mathematical identity allows us to derive the relationship between temperature and pressure inside a hydrostatically ordered atmosphere. So if at a given point inside Earth's troposphere we know the pressure, we can derive the temperature, and vice versa. They are not independent variables. We are now in a position to address a reasonably profound scientific question. Everybody knows that hot air rises. Why is it then that as we rise in altitude in the troposphere, air actually gets cooler? That air cools significantly as it rises within the troposphere can be confirmed by simply taking an aeroplane flight and noticing the external air temperature reading, or by looking at the top of a really tall mountain. such as this one, Mount Kilimanjaro, which is quite close to the equator. As a gas packet expands, it is pushing away the surrounding gas. This requires energy. Where can this energy come from? Well, it can't come from outside the gas packet, so it must come from inside the gas packet. There's only one place where it can come from, and that's the thermal energy of the gas packet. So, as the gas packet expands, it must get colder. Conversely, as the gas packet contracts, it must get hotter. And that's it. We now know how to explain why air gets colder as it gets higher. We can also use our mathematical formalism to derive the form for temperature as a function of altitude inside a hydrostatically ordered atmosphere. Using the ideal gas law, we can transform the incremental change in pressure with altitude, given all the way back in the first slide of this presentation, into an incremental change in temperature with altitude. We can then turn this into an equation for temperature, which shows us that temperature is a linear function of altitude in the troposphere. We can then confirm this against observations. Now, the form for the gradient of this function, which is called the lapse rate, is more complicated when latent heat effects are included. But nonetheless, the relationship between altitude and temperature remains linear, even when latent heat effects are incorporated into the expression. Looking at the observational plot provided in this slide, we can see that the linear relationship between temperature and altitude begins to break down as we move out of the troposphere and into a region where the assumptions underlying our mathematical analysis no longer hold. Since pressure and temperature are not independent variables, once we know the mathematical form of temperature as a function of altitude within the troposphere, we can determine the mathematical form of pressure as a function of altitude within the troposphere. We can then compare our mathematical models against observed values. Doing so reveals that the mathematical model and the observations are in very close agreement. Thus, we can observationally validate the theoretical treatment presented here. The theory I have derived for you today is the culmination of centuries of diligent theoretical development and painstaking observational validation by some of the greatest scientific minds the world has ever known. So, of course, flat earthers have absolutely no hesitation in dismissing it entirely. As we saw in the last episode, Spurs Chemo simply denies that there is such a thing as pressure variation within the atmosphere. The basis for this claim is still somewhat tenuous, but he clings to it nonetheless. However, it turns out that there has been a schism in the flat earth community. Here we join Nathan Oakley in the middle of one of his regular masturbatory sessions.
Do we agree that there is a pressure gradient?
How did you get that pressure in the first instance?
Guys, hold on. Let him
You're
get
a
to the
wily
end.
one.
Let him get to the end. We are all in agreement, Jazz. Yes, there is a pressure gradient.
It seems somewhat strange that Nathan had not chosen to share that particular pearl of wisdom with his colleagues somewhat earlier. In particular, it seems a little rugged that Spurs Chemo is out there spreading the word, only for Nathan to completely undercut and humiliate him in public. But fortunately for us, Nathan goes on to explain the reasoning behind his conclusion that there is indeed a pressure gradient in the atmosphere. Apart, of course, from instrumental records, because God knows nobody's going to listen to them.
A story that we were all taught in about 7th grade about gas cycles. They're produced at ground level. So at 35,000 feet, how many trees are there at that altitude producing gas? Just out of interest. Is it none at that altitude? So there's less gas being produced, therefore less gas.
You have to hand it to Mr. Oakley. He is very thorough. When he is wrong, he is just completely and utterly wrong on every conceivable level. The only thing he got right in that insane, rambling utterance is that there are no trees at 35,000 feet. Let us start at the most fundamental level. Trees, and plants in general, do not create gas. Plants take 6 moles of carbon dioxide and 6 moles of water, and they create 1 mole of glucose and 6 moles of oxygen. At the beginning and the end of this process, which is called photosynthesis, there are 6 moles of gas present. There is no gas destroyed, there is no gas created, the amount of gas stays the same. And if Mr. Oakley had progressed his education beyond the 7th grade, perhaps he would know this. Returning our attention to the case of a reservoir of a hydrostatically ordered fluid, we now allow there to be an inlet at the bottom of the fluid and an outlet at the top. How does the insertion of this fluid flow impact the distribution of the weight of the fluid? It does not. There is still more fluid overhead when one is at the bottom of the reservoir and less fluid overhead as one approaches the top of the reservoir. The pressure is unchanged. Similarly, if we reverse the direction of flow, the pressure gradient within the reservoir is unchanged. It's a spurious argument with no explanatory power. So with that out of the way, let's wrap things up. I do understand that there was a lot of mathematical detail in today's video, but you shouldn't fixate on that too much. The general physical principles presented are relatively simple and intuitive. The first point is that the pressure at any point inside a fluid is strongly dependent on the weight of the overlying fluid. So if you're deeper in the fluid, there's more overlying material. The greater the weight, the greater the pressure. If you're near the surface of the fluid, there's less overlying material and less weight, less pressure. The second takeaway is that from the principle of conservation of energy, it follows that as a packet of gas in the troposphere expands, it must cool in order to provide the energy necessary to push the surrounding atmosphere back. As a result, air temperature within the troposphere decreases as a near-linear function of altitude. The third takeaway is that within Earth's atmosphere, pressure and temperature are interdependent. If we know the value of one, we can calculate the value of the other. The fourth point, and arguably the most important, is that all of the mathematical derivations here and the principles derived from them have been extensively tested against observations and experimental data, and all of them have been found to agree with what is observed in reality. So that about wraps it up from me. Thank you so much for sticking with me through all of that. I really do appreciate it, and hopefully you'll be back next time when I discuss entropy and why Earth's atmosphere doesn't require a container.